So what I'd like to talk to about today is the density management studies. Its title sort of morphed with the onset of the density management studies. It's actually fully entitled the Density Management and Riparian Buffer Studies. And initially, the density management studies was originally designed to look at alternative thinning regimes, as John Tappener described yesterday. But it was realized early on that there was a potential to couple the study with additional work that would look at the impacts of thinning on riparian habitat values, riparian conditions, and the implementation of vegetative buffers to mitigate the effects of thinning on those habitat values. So with the onset of the Northwest Forest Plan, there were some buffer widths that were delineated in the Northwest Forest Plan, and they were set up as interim guidelines. And basically, these interim guidelines were established, but the intent all along was to evaluate those interim guidelines to better determine what the actual buffer needs were on these types of streams associated with, in this case, with thinning and harvest impacts associated with thinning. So what I'm going to talk about a little bit today is the initial implementation and findings from a density management and riparian buffer study with an emphasis on the microclimate characteristics. I'm going to then transition to where we're kind of heading more recently, where we're trying to evaluate stream temperature TMDLs, or in other words, the total maximum daily load for thermal inputs into streams, and what's the relationship between thinning practices and TMDLs. And then also, I'm just going to wrap up with a brief description of where we're going in phase 2 of density management studies. So initially, thinning, the way we conceived of the thinning was potentially as a tool for riparian habitat restoration, as well as compatible production of wood. So what's the level of compatibility between thinning for wood production and the ability to use thinning as a method for habitat restoration. And so the strategies that were outlined in the Northwest Forest Plan dealt with conservation, they dealt with riparian reserves that were really designed to conserve the diversity and maintain habitat and water quality, and as Dee Dee spoke to yesterday afternoon, provide some connectivity at watershed and landscape scales. But then we're applying this thinning to these areas, and basically through that thinning, we're modifying the overstory canopy, which in turn will alter the understory environment and generate some understory vegetation and structure responses. And so we're interested in understanding how that type of consequence can lead to either enhanced riparian habitat and function, or does it actually cause a detriment to habitat and function? So the first question that we're really trying to get at is how wide should stream buffers be? And most of you have seen this diagram, which was taken from the FEMAT document. And basically, this is a conceptual diagram that was used to guide the development of the interim guidelines. And what it shows basically is how does the influence of an edge or a harvesting impact the microclimate within the untreated portion of the forest. So what we're illustrating here in this diagram is the conceptual idea of how far into a retained stand would you have the influence of a harvest. And so this diagram shows what the perceived distance of effect would be in terms of soil moisture changes, radiation changes, soil temperature changes, air temperature, wind speed, and relative humidity. Our study actually addresses 4 of these different characteristics: soil temperature, radiation, air temperature, and relative humidity. So our purpose behind undertaking the microclimate and microsite component of this study was to describe some of the spatial and temporal variability, to evaluate the responses to upland density management treatments and riparian buffer widths, determine potential ecological linkages between these measured changes in microclimate and microsite attributes, and the diversity of aquatic and dependent vertebrates and other lichens and bryophytes and other elements of diversity. And then also to develop some methods for monitoring spatial and temporal variation in riparian microclimates. So the DMS microclimate and microsite monitoring component has been addressed at a total of 7 DMS sites to this point in time. And for those of you who are somewhat new to the density management, there's actually a total of, I think, 13 different sites. So we're actually doing this activity at a subset of sites. And for those of you who are aware of the initial thinning component of density management, these sites are the initial thinning component of the treatment or the study. So what you can see is our sites range all the way from sort of the Delft Creek area, Keel Mountain. So these are our Cascade sites. Then we have more sites down here in the Coast Range and sort of this transitional bottom line site. So for those of you who weren't here yesterday, just to give a brief overview of the density management study layout. A typical layout is illustrated here for Green Peak, which is also where you'll be going on the field trip tomorrow. What this diagram illustrates is we have a control thinning unit, we have a moderately thinned unit which brought the initial density down to 80 trees per acre. We had a high residual density thinning unit which brought it down to 120. And then we have a variable density unit which basically divided a treatment area into thirds, with roughly a third being thinned to 40 trees per acre, a third to 80 trees per acre, and a third to 120 trees per acre. Embedded within these different treatments, overstory thinning treatments, were some substand level structures, either being leaf islands of a quarter, half, or 1 acre in size, or gap openings or patch openings, again in sizes ranging from a quarter, half, to 1 acre in size. Embedded within this diagram, you can see 3 stream reaches that illustrate a range of buffers that were imposed to evaluate. In the case of Green Peak, we had a 1 tree height buffer, a variable width buffer, and a streamside retention buffer. So as a result of the implementation of the treatments, we can see here sort of the range and overstory conditions that resulted from the initial treatment. And so we see in an unthinned stand, and these data were collected actually 3 years after implementation. But we see that in the unthinned stand, we have about 9% visible sky. In the 80 tree per acre, 28%, 40 tree per acre, 38%, and 1 acre patch, 61%. So it's important to know that using the hemispherical photography methodology, a 1 acre patch, which is essentially a small clearing, you still have only 61% of the light being transmitted due to the edge effects that are picked up in this methodology. To repeat, the buffers that were analyzed consisted, within the density management studies, we had a few sites that had 2 tree height buffers, and most of the sites had a 1 tree height buffer. These 2 buffer delineations are what came out of the interim guidelines for the Northwest Forest Plan. So these we considered to be fairly conservative buffer configurations. Alternative buffers that were considered in the density management study consist of the variable width buffer and the streamside retention buffer. Variable width buffer has a 50-foot minimum, but it would extend out further to encompass distinct riparian features, local areas of concern where you might have sensitive species or sensitive vegetation, or distinct slope breaks where you can distinguish the riparian from the upslope condition. The streamside retention buffer had a 20-foot minimum, but basically was retaining all trees that had a portion of its canopy extending out over the stream channel. In our study, we're reporting on, we used a series of transects running from the stream into the upslope, and illustrated here is just the average, kind of a conceptual diagram of the average buffer width for the streamside retention variable width and 1 site potential tree height buffers. So for as an example at Green Peak, this slide illustrates the array of transects that were used to capture data on the various forest conditions prior to and following the actual implementation of the treatments. One thing to note here, I'll be referring to these cases as kind of a special case where we have a buffer extending up into a patch opening as a separate treatment from a buffer that extends just into the thinning, a moderate density thinning area. So I just want to quickly summarize what we saw in what we're calling phase 1 of density management studies, which is sort of that initial pre-treatment followed by 3 to 5 years of post-treatment monitoring. And just to point out some of the obvious responses, so when we look at the amount of light that was being transmitted through the canopy, or what we're able to see when we look up through the canopy, this slide just illustrates the range of light conditions that were retrieved under the different treatments. So you're going to see a series of slides and they're all organized the same way. Basically, you have the stream zone, what we measured in the buffer, and what we measured in the upslope. And the symbology here kind of goes in increasing intensity of disturbance. So we have the unthinned, we have a 1 tree height buffer into a thinning, and a 1 tree height buffer into a directly adjacent patch opening, and those are 1 acre patch openings. Similarly, we have a variable width buffer into thinning, variable width buffer into a patch, and then we have the stream side retention buffer into a thinning. So what we're showing here in this slide is actually the basal area responses, and as you'd expect, the thinned units, we didn't thin in the buffer, but when the sampling method that was used, because the stream side retention buffer is so narrow, we actually picked up the influence of the upslope thinning in that measure of basal area. But it just shows that the thinning units here in the upslope obviously drop basal area, and the patch openings do what you'd expect. You drop the basal area. Where it becomes a little bit more interesting is when we look at some of the light responses associated with those changes in basal area. Obviously, we didn't thin in the stream, but what we're seeing in terms of light, visible skylight, is our narrowest buffers, either the variable width adjacent to a patch or the stream side retention, we have a significantly higher amount of visible light at the stream. We also have a significantly higher amount of light in the buffer. And then we get some separation of thinning and patch openings in the upslope. So what did this mean in terms of maximum air temperature? So when we look at this information here, basically in terms of maximum air temperature, so this is maximum mean daily air temperature as measured in the summer, basically where we're getting responses then. At the stream level, we're not really seeing much differentiation among the treatments, but this stream side retention buffer is significantly elevated relative to the other treatments. When we look in the buffers where we're seeing differences, the 1 tree height buffer is not showing any elevation relative to the control, but we do get some separation of treatments when we throw in a patch opening adjacent to those buffers, or when we have a narrow stream side retention buffer. So again, at the stream, we're not measuring that effect except at the stream side retention. Within the buffer itself, we're getting an elevation of temperature when we have patch openings adjacent to the buffer or a very narrow buffer. And again, in the upslope, remarkably what we get here is we're showing separation or differences in temperature with these patch openings in the upslope. So obviously when you make that clearing, you get higher temperatures relative to the thinned area or the control. We can also look at this kind of response in terms of something like soil temperature. And actually, at the stream, it's not really soil temperature. What it is it's the temperature sensor embedded just below the surface of the stream substrate. So we're getting this mixing of water and stream substrate. And basically, we're not seeing any elevation of temperature there. We're not seeing any elevation or separation of soil temperatures in the buffer, but we do get separation of soil temperature when we create patch openings in the one tree height buffer. And you can think about that a little bit. Why don't we get it in the patch opening in the variable width buffer, or in the patch opening associated with the variable width buffer? You have to realize that this patch opening is located lower down in the channel on the side slope. Because of the extent or the width of the one tree height buffer, this is occurring higher up on the ridges. So basically what we found in that first phase was basal area in young Douglas fir stands had to be substantially reduced in order to achieve light levels that will potentially stimulate understory vegetation. I guess I didn't include the understory vegetation in this talk. Differences in microclimate along transects with different buffer widths and upslope treatments tend to occur only during the warmest part of the day and in the upslope treated zone. And then microclimate is moderated within approximately 10 meters of the stream, regardless of upslope density treatment, when you have a buffer with a minimum of 15 to 25 meters. So we're going back to that variable width buffer that actually had a minimum of 50 feet. So where we've gone from that point in the first phase, more recently we've begun to ask the question as whether or not density management study can be used to assess thinning impacts on water quality. And again, we're trying to get at some of the issues that have arisen with monitoring to meet TMDL requirements for stream temperature. And I'm just going to briefly summarize what we've done here. From the DMS study sites, we actually have 9 reaches that we evaluated with respect to some parameters that are associated with shade and microclimate and water temperature. So we looked at topography, and we also looked at stand structural characteristics. And basically what this diagram simply shows is for the 9 reaches that we've done some detailed assessments, this is the array of channel cross sections. And what you're seeing here, as you look upstream, there are actually 4 transects, and that's actually the array of channel cross sections represented by the 4 transects that are arrayed up the stream. One of the things that we did along these was we made measurements of angular canopy density, which is a measure of the amount of canopy coverage, or the amount of occluded space associated with the canopy at different solar angles. So representing solar angle early in the morning at 6 a.m., looking again at 10 a.m., noon, 2 p.m., and 6 p.m. From that assessment, basically we did correlation analyses on those, and I'm not going to present all the correlation matrices or whatever, but basically what we came to the conclusions, preliminary conclusions, based on these 9 reaches was that topographic shading is an important element of stream shading in headwater streams. Streams with general east-west orientation or steeper side slopes tend to receive more topographic shading. The effectiveness of vegetation shading increases with tree height and canopy density. But the relative importance of topographic shading as compared to canopy shading is really difficult to discern, particularly in these areas with high density canopies and relatively uniform canopies. So in these upper headwater streams, we really didn't have a lot of variation in the amount of canopy cover over those streams, even in the thinned units. So what we've done now is we've extended this to include operational sites over the last year or so, and we're trying to expand the scope of inference by looking at some of these characteristics of shading and temperature response at both the experimental DMS sites, but also some operational units on BLM lands. And we're seeing a lot of variability in the stream temperature patterns, unexpected relationships among some stream temperature and thinning and buffer treatments. And the question that I have is there potentially a stronger coupling between shade and microclimate than between shade and water temperature? And then to what extent does hydrology and topography potentially trump forest structure influences on stream temperature in these managed headwaters forests? And my last little slide here is where are we going in density management with phase 2? So recently, within the last 3 years, most of the sites that we dealt with early on in phase 1, we've gone in and re-thinned. So now what we've gone is originally there were about 240 trees per acre. Our initial treatments brought them down to about 80 tree per acre in the moderate densities treatment. And recently we've brought those densities down to 30 trees per acre. So the question here is, do buffers that seem to mitigate the effects of thinning effectively when you thin to 80 trees per acre, when you challenge them by thinning down to 30 trees per acre, what will be the consequences? Will those same buffer configurations be suitable? And there we go. I'll just leave it at that.